Okay, so there's an interesting question in your book. So the question is this. You are swimming in a lake. The lake is running at constant velocity. Nehirde yüzüyorsunuz. Nehirde sabit bir hızla akıyor. You are swimming counter the current. Akıntıya karşı yüzüyorsunuz. Karşı. And for an observer standing on the shore, you are not moving. In this reference frame, is there a work done on you? Or are you doing any work? First of all, are you doing any work? Okay, how many of you say yes? How many? So, did everybody hear the question? You are swimming there's a river, and you are swimming in the river, trying to go counter the current. So, the water is trying to carry you in this direction. You are trying to swim in this direction. Okay? I'm standing and looking at you, and I see that you are always over there. Am I? Am I what? I'm standing here. Just imagine that there is this river over there. I'm just standing like this, sitting down. And you are just trying to swim in this direction. I'm just looking at you and laughing how you cannot move at all. So are you doing any work? So who says yes? Okay, those who say yes, can you move to this side? This side is yes, this side is no, and I want everybody to move to some side. This side is yes. Yes is over there. No is over there. Yes over there, no over there. No, tarafsız bölge yok. I want everybody to choose either yes or no. There is no forcing other people to say yes or no. Everybody should use their free choice. Yes over there, no over there. I want everybody to move. I want this block to be empty. Everything included. I mean, it's just translational motion. Okay, I want this block empty. You can change sides if you like. You are free to move from one side to the other side. So this side is yes, this side is no. Why yes? Any one of you? Anyone? Well, if you are saying no, you should go to that side. No, I want you to explain why you are saying yes. I will ask them why they say no. So do you all agree with those answers? Do you have any other answers? Why no? No, you are always talking. Why no? Somebody else, okay. Okay, hold on. They said that there is displacement. Now you are saying that there is no displacement. What's your point? So you are saying there, well, the definition of the force of the work doesn't, so you are saying net force is 0. Okay, so one thing is, okay, one of you is saying net force is 0, the other one is saying net displacement is 0. Okay, but they say that there is displacement. You are saying that there is no displacement. First, let's agree on that. Is there a displacement or not? Yes? What do you think about that? You are free to move to that side if you are convinced. Or you are free to move to the other side if you are convinced. Okay, so there is one explanation why there is no displacement. Yes? In the same reference frame of the swimmer, you mean? Okay, so what is your objection? So their claim is you should calculate the work in the reference frame of the river. So, is that right? Okay. No, you said no? The river is also an inertial reference frame. It is moving at constant speed, constant velocity. What do you mean? Well, I can measure. I'm not in the river, but I can measure the velocity of the river and find that the velocity is moving at constant speed. Since I know that I am an inertial reference frame, it is another reference frame that is moving at a constant velocity relative to an inertial reference frame. So that is an inertial reference frame also. So they are claiming that the force is zero. So what do you think about that? So since the swimmer is moving at constant velocity, they say that the force is zero. So even if delta R is non-zero, since F is zero, the net force is zero. Okay. Okay. So if net force is bigger than zero, then according to you, the swimmer is accelerating. But if it is accelerating, since the river is moving at constant velocity, it should also be accelerating according to me. Yeah, so, but I see him always over there. He's not moving at all. He has constant speed in relative to my reference frame. Okay, now you can go back to your seats. Both of you have some right answers, by the way. Now, I would like to give my answer to this question. We talked about delta R. Now, in the first weeks of this course, we also talked about relative coordinates, relative velocity with respect to different coordinates. We also talked about the position relative to different coordinates. I said that, okay, your friend sitting here can be 5 meters in the x direction according to this reference frame, but he will be 7 meters in the y direction in this reference frame. So to start with, this delta R depends on which reference frame you choose. Will you be talking about my reference frame that I'm just sitting on the seashore, or in the reference frame of the water. You should first specify which, or in the question it should be specified, which reference frame are you talking about. That is the first thing you should do. And your answer, since this delta R depends on the reference frame you choose, the work done that you calculate will also depend on the reference frame you choose. So it will be frame dependent. The work done is a quantity that depends on the reference frame. Well, the force, acceleration in inertial reference frames are frame independent. We know that if an object has zero acceleration in one reference frame, he has the zero acceleration in all inertial reference frames. That is the definition of an inertial reference frame. But it also holds for any object with a given acceleration. If an object is accelerating in one inertial reference frame, it is also accelerating in every other inertial reference frame. So force, which is the mass times the acceleration, doesn't depend on which reference frame you choose, but it depends, what this delta R depends on the reference frame that you are talking about. Now let's see. In my reference frame that I'm sitting here, the work done, the net work done on my friend, where are you, swimmer? Yes, on him as he is swimming, the net work done on him is 0 because there is no displacement. Since he's just staying there at constant velocity, 0 constant velocity, the net force acting on him is still 0, so the force is 0, there's no net work done on him. In the reference frame that goes with the river, or in the reference frame in which the water is at rest, of course, my friend is moving in that direction up the river. He's swimming up the river in that reference frame. There is a delta R in that reference frame is non-zero. That's a different reference frame. Delta R is non-zero in that reference frame. But still, his speed is constant, so the force acting on him, the net force acting on him is still 0. But the net force has at least two components. The force that he creates while he is swimming, and the force that the water exerts on him, this drag force. These two forces in both reference frames, these two forces are in opposite directions. In this reference frame where I'm at rest, since delta R is 0, both of these forces do not do any work. They do 0 work, both of them. In the other reference frame, moving with the water, delta R is non-zero. My friend is moving, he's just getting away from me. He will be getting away from me. Now, if we talk about the work done on him by the drag force, it will be negative because the drag force is trying to bring him towards me, whereas he is moving in the opposite direction. So the scalar product is always negative. The work done by him on himself while he's trying to swim, he's creating a net force on himself, which is the friction force, by the way. It's also the drag force. The drag force exerted on his hands as he's swimming. That drag force will be pointing in that direction, and he's also moving in that direction, so that force will do some positive work. The net work will still be 0 because since he's not accelerating, the drag force due to the flow of the river and the drag force due to his stroking his hands, they will be equal in magnitude, opposite in directions. So whenever you are talking about the work, you have to be careful. The work done by which force? That is one thing you have to consider always. Is it the net work done on the object or the work done by just one force acting on the object? You have to be careful. First, you have to fix your reference frame. There is no correct or wrong reference frame. As long as it's an inertial reference frame, it is a correct reference frame. You can choose any reference frame you like. And the work done, in general, will depend on which reference frame you use. So if you obtain some work, your friend obtains some other result for the net work done. You can both be wrong if you have chosen different reference frames. So you have to pay attention to which reference frame you are talking about. You have to be careful about which force you are talking about. Of course, you should always be talking about the forces exerted on your mass. In the case of this sliding book, there are many forces in action there. As I'm sliding the book, there is a friction force acting on my book, so I can talk about the work done by the friction force on the book. But there is also a friction force exerted on this table. So I can talk about the work done by that friction force on this table. You should always specify which force acting on which material and in what reference frame. You should pay attention to all these things. Any questions? You had some other question, but any questions on the swimmer? Well, a similar example. When you are holding this book, you will not be able to hold this book indefinitely. After, I don't know, let's say 10 minutes, your arm will get tired. You will get tired. So you feel like you are doing some work. But this definition tells us that you are not doing any work. Why do you get tired? I think it's the same question, right? Or in the swimmer example, if you ever try to swim against the current, you realize that you get tired quite fast. So that means you are wasting some energy. You are using some energy. But you are not doing any work, so where does that energy go to? Kind of. But I will postpone this is a question for you to think about. I will postpone it until we finish our discussion about the energy. We didn't yet talk about the potential energies, internal energies. Now, just wait a few more weeks and ask this question again. Until now, we had only defined the kinetic energy. That is the only energy we defined. You had another problem. Is your question related with the swimmer? Okay. Current. Okay. So what's your question? He will just swim? In which reference frame? In which reference frame? Well, there was one comment over there. You were saying that the work should always be calculated in the reference frame of the object. Now, if you calculate the work done in the reference frame of the object, you are never moving in your own reference frame. In the reference frame fixed on you, you are always at rest. You cannot go away from yourself. So in your own reference frame, delta R is always 0. So if you are an inertial reference frame, if you calculate the work in your reference frame, the work done on you will always be 0. So whenever you are talking about the work, you should better not talk about the reference frame, your own reference frame. Most of the time it will not be an inertial reference frame anyway. So which reference frame are you talking about? From the water, or me just standing by the pool and looking at the pool. So what will I observe? Swimmer will be moving. Delta R is non-zero. So which work are you talking about? The work while he is swimming at constant velocity, or the work during the time interval that he started at rest from one side of the pool and then went to swam to the other side of the pool? Okay, from one side to the other side. At the other side, he's swimming. Is he still swimming, or he started from one side, started swimming, and on the other side he's just resting. Okay, so that is kind of easy. We had already shown that the work done on an object, the total work done is the change in the kinetic energy. So you are saying that the initial kinetic energy is 0, final kinetic energy is 0. So the change in the kinetic energy is always 0. Work done on him is 0. Well, that example is identical to the example of the book. You have initially the swimmer at rest. He then accelerates. He reaches some velocity and continues swimming at that constant velocity. So in the initial part, while he is accelerating, a net positive work is done on the swimmer. Then he is moving at constant velocity. During this time, there is no net work done on the swimmer. Then he reaches the other side. He slows down and just stops. Then there is some net negative work done on the swimmer. But the total work will again be 0 because there is no change in the kinetic energy. This is the total work done on the swimmer. What about the work done by the swimmer? Yeah, the work done by the swimmer is positive. So he will get, I mean, that's kind of intuitive that he gets tired because as he's swimming, he's pushing water towards his back. That's how he goes forward. He's exerting a force in the backward direction. The water is displaced in the backward direction. So the net work done on the water is negative by the swimmer. It's positive, sorry. The work and the displacement and the force are both in the same direction. So the swimmer does positive work on the water. Then of course, as it displaces the water, the displaced water will have some finite velocity in its environment, but the environment will also exert this drag force on this displaced water. So eventually it will also stop. Eventually the net work done on the water of the pool will also be 0. But the work done by the swimmer only on the water is non-zero. So this is why you should also always make this distinction. Are you talking about the work done on the swimmer, the net work done on the swimmer, or the work done by a particular force on the swimmer? Or are you talking about the work done by the swimmer on the water? Yes, you had some other question. Jump. Take the elevator. Stand. You can say also in Turkish, I will translate. Now, her question is this. While you are standing up, you are exerting a net force on yourself. Well, the earth is exerting a force on you, which is vertically upward. As you are moving around, your displacement is always in the horizontal direction, whereas the force that is exerted on you is always in the vertical direction. So you are never doing work. So is that the question? So you are never doing any work. So is this true or not? When are we doing some work? Well, when I'm accelerating, I'm exerting, there is a net force exerted on me in the horizontal direction. So there is a net work done on me as I'm accelerating. When I stop, the network, the work, as I stop, the work done on me is negative. If I start moving and stop moving, the net work done on me by external forces is 0. The net work done on me by external forces will always be 0. If I'm just moving at constant speed, then make a right turn at constant speed. So is the work done on me 0 or positive or negative? I'm moving at constant speed. Take a right turn. Which means? Okay, so negative, 0, positive. Onu biraz daha tartışırız. Okay, so the answer, the question is this. I am moving always at constant speed. Okay? Not velocity, speed. Then I just take a right turn. I'm doing a circular motion. So we have already studied circular motion. We had some demonstrations upstairs about circular motion. So the work done on me, the net work done on me as I'm taking this left turn, right turn, is it negative, this block, 0, this block, positive, that block? At constant, I'm always moving at constant speed. My speed is always constant. So did everybody choose their block, which block they are in? So everybody here in this block is saying that the net work done is 0. Is that true? Shh, don't answer yet. People are still moving around. Everybody in this block says that the work is negative. Everybody in this block is saying that the work is 0. Everybody in this block is saying that the work is positive. Now, as I start here. I'm moving at constant speed, and I end my motion here, again at constant speed. During this time interval, the work done on me is positive, negative, or 0. Positive, those who say 0, and those who say negative. This is negative. I'm repeating the question. Well, this time in Turkish. Sabit hızda gidiyorum. Vektörel hız değil, sabit hızda gidiyorum. Sağa döndüm. Şimdi şuradan şurada sabit hızla geçeriyordum. Buradan başlayıp döndükten sonra şuradan geçtim. Bu süre zarfında, bu süre içerisinde belli bir delta arım var. Bu süre içerisinde bana yapılan toplam iş, benim üzerime yapılan toplam iş negatif mi, sıfır mı, pozitif mi? Well, does it change the sign? It will not affect the sign of it. So did everybody move to their answers? This block is negative, this block is positive, that block, no, this block is 0. That block is positive. I will just pick somebody from the last 2 rows with students in them to answer. Last 2 blocks. Last 2. You sit there. So is everybody sure about their answers? So are you determined about your choice? Is your final chance to change your blocks? Okay, so I will start with this positive block. So why do you think it is positive? You on the corner? Okay, you just tossed coins. You? She is running away. You? Okay. Yes. The swimmer. Why? You don't like the negative answer? Okay. No. Well, you. Okay. Okay, that is one answer. In the same direction. Okay, there's another answer. You agree? Now I'm at constant speed. Okay. Okay, so I will summarize your answers. Well, you like the positive answer. Also, you are saying that there is a force, there is a displacement. So, and they are in the same direction. The force and displacement are in the same direction. So the network is positive. That is your answer. So do you want to add anything to this? So, okay, again, you are saying that the net force is non-zero, and while we are turning around, we're taking the curve, there is a net force, and we are doing some work due to this net force. Okay, so that basically summarizes your answer. Okay, let's come to negative. Why do you think it is negative? Okay. I'm moving at constant speed, so the velocity can never be 0. The speed is the magnitude of velocity. Okay. I'm turning to the opposite direction with constant speed. And I never stopped. So, sure. Negative, okay, negative force, what do you mean negative force? Now, a vector cannot be positive or negative. Okay, so the force is in the opposite direction as the velocity. So how does it enter into this definition? So you are saying that the force is also in the opposite direction of delta R? So in that case, we would have negative work, of course. Okay. Okay. So, how do you apply that to this definition of work? For example, in the other side in this positive block, they said that the force is in the same direction of delta R, so the net work is positive. So, are you claiming that the work is in the opposite direction of delta R, so that the work is negative? Okay, so here's do you want to add anything to this? Or are you convinced with this answer? Yes, okay. So there's another answer. On one side says that the force is in the same direction as delta R. The other side says that the force is in the opposite direction of delta R. So who wants the answer in this block? Somebody else? Somebody over there who wants to answer? Why do you think the work is 0? Or were you just too lazy to change blocks? Now I start from here, I'm here. Another answer. There is one difference though. Since I'm turning around, I'm making circular motion. There should be some horizontal force acting on me. In the case of the book, if I'm carrying it with constant velocity, the net force was 0. But in this case, I'm not carrying it with constant velocity. I'm carrying it with constant speed and then taking a curve. This is the difference. So there is a horizontal component of the force. And this side claims that that component is in the same direction of delta R. The other side claims that it is in the opposite direction of delta R. So you came here now? Okay. Okay, so the displacement and the force at each instant are perpendicular, you mean? So there is this answer over here. They say that as I'm taking this circular motion, there is a force acting on me, but this force is always perpendicular to the displacement. Then you should sit over there. No? So what do you think about that answer? I'm taking this curve. I'm making some circular motion. Okay, so the force acting on me, the net force acting on the net horizontal force acting on me, should be perpendicular to my velocity because my speed is constant. If it is perpendicular to my velocity, it is always perpendicular to the displacements. The direction of the force, you mean? No, okay, we did study circular motion, right? You know that the acceleration is always perpendicular to the velocity vector. So the force is always perpendicular to the velocity vector. So now, what is your answer? Objection? Okay, this is my direction of the velocity. This is my velocity. Or let's say I'm moving in this direction. This is my velocity. My if I'm taking this left turn, this is my acceleration. So this is the direction of my force. And these two are at 90 degrees. Okay. I will just make, as I turn, the force will always stay perpendicular to the velocity. The force is also changing its direction. So they will always stay 90 degrees, at 90 degrees. So the force will be always perpendicular to my displacements. If the force is always perpendicular to the displacements, then the work done is 0. Well, this was an example of a variable force. The force is always changing. So just imagine we have this curve. You can apply it to this circular motion. Now, since the force is changing, we cannot really use the F times the delta R expression. Now, this expression is valid if the force is constant. That is what we had derived also here. This is the definition for constant force. Now, for variable force, we cannot really use this expression, but still what we can do is just divide this into very small parts, just as we did in the beginning in our demonstration. And each one of these very small segments, the work done, the force is almost constant. This delta L, so for this segment we can define the work. The work done in this segment is given by this expression. Now, in the special case of the circular motion, this is our circular motion. At some point we are here. This is the force acting on my system, since it's doing a circular motion. Well, in this very small segment, there is a displacement dl in time delta t. The work done in this very small segment will be equal to f dot dl, let's just put dt, f dot dl. This is the definition of the force we have. Now, if I divide this by dt and multiply it by dt, the work done in this very small segment will be just the force scalar product. Well, this is the velocity vector times dt. Now, for circular motion, the force is always perpendicular to the velocity. So for circular motion, the work done is 0. Well, this is one way of saying it. Another way of saying it is this one. The net work done on an object is always equal to the change in its kinetic energy. Since, although I am just moving on a curve, there is a net force acting on me in the horizontal direction. I'm moving at constant speed, so my velocity is constant. So my kinetic energy doesn't change. So the work done on me has to be 0. So those who would like to change their answers now can change their answers. The remaining we should continue discussing. So do you want to, this is the answer. All these people say that the work done is 0. So you still insist that the net work done is positive? Now, the problem is the counterintuitive definition of the work done if you apply a force in a perpendicular direction to the displacement. So in this example of carrying the book, one of you had said, if I'm carrying this book around at constant velocity, I'm not doing any work. I'm not doing any work on the book. It is counterintuitive because you do feel that your arm gets tired. But since the force and the displacement are in opposite directions, in perpendicular direction, the net force, according to this definition, the physical definition of the work done by you is 0. You do get tired because of the way the muscles work. The muscles do not really work. I mean, when you hold it like this, the mechanism in your muscle isn't really at rest. The muscles constantly contract and relax, contract and relax. While they are contracting, they are exerting a force in this direction. So your muscles are doing some internal work, not on the book. So your muscles are still doing work, and that is why you are getting tired. But you are not doing any work on the book. The work that you do is somewhere else. So, okay, so there are fewer people over there. Do you still think that the work done is negative? Of course. Do you still think that the work done is positive? Okay, so let's start with you. Why do you think it is still positive still? Repeat it again. Okay, so I'm moving at constant speed, first linearly, then I take a left turn and continue linearly. Here I have a velocity, let's say v0. Here I have a velocity in this direction, let's call it v1. And we know that v1 is equal to v0 because I'm moving at constant speed. Okay, so this is the diagram we have. During this time, there is a force acting on me in this direction. This is the direction of the force. While the force is pointing in this direction, I have moved from this point to this point in the perpendicular direction. Well, this part is a circular motion. After that, I'm just moving continuously. But even for this part, is just one part of a circular motion. By the way, our time is up. Those of you who would like to continue discussing, we can just continue outside. If you have other courses, other lectures, see you on Thursday.